Imagine your community has just raised the funds to build a brand new agricultural market. You need a place to bring local crops to sell. But before anyone pours a single bag of cement, you need to find the perfect spot to build it. You might think a quick hand-drawn sketch of the area is enough to get started, but a simple drawing won't tell you if you're accidentally placing your foundation in a sinking swamp or crossing over into another district's land. Take a look at the actual landscape. We have a complex patchwork of farming fields pressed right up against treacherous wetlands. To safely plan construction here, we need a tool far more precise than a sketch. We need a specific type of map. This layout shows our options. A political map won't work. It only shows human-made boundaries. A physical map only shows nature. But this one, a topographic map, shows both human features and the exact shape of the terrain, like hills and valleys. A topographic map gives us a highly accurate mathematical translation of the real world. By understanding the numbers behind the drawing, we can ensure our project stays on solid ground. Our very first logistical challenge is distance. To estimate transportation costs for the farmers, we need to know exactly how far the new market will be from the main highway. To figure that out, we look at this legend. This tells us the map's scale, which is the exact shrink rate mapmakers use to fit a massive area onto a small piece of paper. As you can see, scale is shown in 3 different ways. First, we have the statement scale. This is a simple sentence that tells you, for example, that 1 centimeter on the paper represents 1 kilometer on the ground. Then there's the linear scale, which looks like a small ruler drawn right onto the map so you can measure distances physically. Finally, we have the representative fraction. It looks like a ratio, such as 1 to 50,000. This means that 1 unit of measurement on the map equals exactly 50,000 of those same units in the real world. So 1 centimeter on your desk equals 50,000 centimeters out in the valley. Here is a demonstration of how to use this. Roads rarely travel in a straight line. By laying a flexible piece of string along the curves of a mapped road, marking the ends, and then pulling it straight against that linear scale bar, we get the true travel distance. By mastering scale, we can accurately calculate our real-world transport logistics from a desk without ever having to walk the entire route ourselves. With distance calculated, we face our next challenge. We need to claim a specific plot of land for the market that is guaranteed to be safe from the nearby swamp. To find that safe zone, we look at this grid. Notice how a network of intersecting blue lines acts as a targeting mechanism over the terrain, with numbered axes running along the sides. To read these coordinates, we use a simple rule. Run along the corridor, then climb the stairs. That means you always read the horizontal numbers at the bottom first, the eastings. Then you read the vertical numbers going up the side, the northings. By combining the 2 easting numbers with the 2 northing numbers, we get a 4-figure grid reference. This gives us the general square where the ground is dry enough to build, but we need to be more precise for the actual foundation. By dividing that main square into 10 invisible segments along both edges, we generate an exact 6-figure grid reference. This pinpoints the very center of our building site. You have to be careful though. If you accidentally reverse the order and read the northings before the eastings, your coordinates will send the construction crew to the completely wrong side of the map. Following the corridor then stairs rule gives us a reliable geographic targeting system. It eliminates all guesswork from the land selection. We have our distance and our exact location. The final local problem is orientation. Which exact direction should the front doors of the market face to catch the early morning sunlight? Looking at this diagram, we overlay a 360-degree compass ring right onto our site. This introduces a system called bearings, which is far more precise than simply pointing north, south, east, or west. Bearings always start pointing straight north, measuring at exactly 0 degrees. From there, the measurement sweeps clockwise through east at 90, south at 180, and west at 270 degrees, until we hit the specific angle needed to face the morning sun. Compass bearings now replace vague verbal directions with locked-in mathematical angles, finalizing the perfect blueprint for our project. The tools we just used to plan a local market don't stop at the district border. As we pull back into space, we can see how map math applies to the entire spinning planet. This model of the Earth shows a global grid system. The horizontal lines wrapping around the planet are called latitude, and the vertical lines running top to bottom are longitude. We use these intersecting lines to find entire countries and oceans on an atlas. Right in the middle is the prime 0-degree line of latitude, the equator, which cuts directly through Uganda. This global measurement is an actual physical place you can visit and stand on. The main difference is that local grid references are drawn as straight lines for flat, specialized maps of a town. Meanwhile, latitude and longitude are curved lines, designed to perfectly wrap around our spherical globe. But whether it's a pilot navigating a cargo plane across the ocean or a community planning a local agricultural market, the logic of mapping remains exactly the same. By mastering scale, grids, and bearings, you gain the ability to measure, locate, and navigate any part of the real world with absolute mathematical precision.